So what I've prepared for you today is a kind of tutorial on the provable security treatment of symmetric encryption. For those that already have seen provable security treatments of symmetric encryption, I hope that I've imbued enough of a kind of recent viewpoint on this subject that you won't be completely bored. And I've included some recent work as well. But overall, I would consider this more of a tutorial-style talk than a latest paper kind of talk. Where's this device? I'm sure you have all seen this kind of diagram illustrating the symmetric encryption setting. In it, some sender and receiver share a secret key, capital K. The sender has some message he would like to transmit to the receiver, and therefore first transforms it into a ciphertext C, transmits it across some channel which an adversary is watching, and the receiver can recover the original message. I myself have drawn pictures like this many times. I'm sure you have seen them all. And yet, I think that there's something fundamentally quite bad about illustrating or describing symmetric encryption in the way that I just did. For one thing, a picture like this already embodies all kinds of assumptions, many of them implicit, and many of them perhaps not what one actually expects in a final definitional treatment of symmetric encryption. For example, this picture would seem to indicate that the adversary is some kind of passive eavesdropper. That's not the way which we will formalize symmetric encryption at all. Inside this little statement would seem to be an assertion that the ciphertext is a function of just the key K and the message M. That also is not what I will ultimately intend. I think we need to take this kind of diagram with a grain of salt. Furthermore, perhaps this is really starting with the wrong thing. It doesn't say what an encryption scheme is. That is, what is the syntax of an encryption scheme, quite apart from the notion of security of the object. That's actually where I will begin. I will try to establish what I mean syntactically that an encryption scheme is, separating it from any notion of security. I think only after you have a notion of what is the syntax of a scheme, what an encryption scheme is, can you really address the problem of formalizing its security. Okay. So in answering these two questions, what an encryption scheme is syntactically and what is it supposed to do, I won't give you just one answer. In fact, my answer is that there is no one answer, that this is highly contextually dependent, and there's a variety of meaningful responses according to what is your actual intent. I will illustrate some of the space of what encryption schemes are syntactically and semantically in the symmetric setting. When I describe encryption schemes to you, when we actually construct them, I'm always going to start with the same primitive. We'll start with a block cipher, highly unoriginal. We will turn our block cipher into our symmetric encryption scheme. Here is an attempt to do so. This is the, whoops, it's mislabeled. This isn't an encryption scheme at all. This is the CBC MAC. We're going to turn our block cipher into the object we're trying to construct. For us, there will be encryption schemes. In this picture, it is a particular message authentication code. When I turn a block cipher into a higher level primitive, I call this a mode of operation. Okay? We will be looking at some modes of operation and trying to differentiate their worth. This is not a formal notion, yeah? I don't know, if I threw into the mode of operation not only the block cipher, but rather complex algebraic primitives, you might want to cease calling this a mode. And yet that doesn't seem to be something formally meaningful to separate. The provable security paradigm is what I'll be applying throughout today's lecture, and I think in most or all of the lectures that follow. Rather than immediately jumping in and giving some protocol, some mode of operation for an encryption scheme, what we will do is first try to distill out a definition, D, for the problem at hand. The definition is quite separated from the scheme, from the protocol, and you should not be thinking in terms of the scheme in coming up with the definition. This task of coming up with the definition is a very difficult one. It is certainly as intellectually significant as designing schemes. And I want to spend a lot of time focusing on how we do definitions in this realm. Once we have a definition and a protocol, now we should be in a better position to demonstrate that this protocol is correct. Ideally, we would just exhibit a proof showing that this protocol satisfies this definition. Typically, we're unable to do this. We're unable to do this because usually in demonstrating that a protocol pi meets some definition D, we would already have done something like separating P from NP or some kind of concrete alternative along those lines. So instead, we will give some other definition, little d, and some other protocol, little pi. And the proof will take the form of a reduction. The proof will show that if protocol little pi satisfies its definition, little d, then in fact the higher level protocol, capital Pi, satisfies its definition, capital D. All the proofs which we will describe today can be thought of as existing in this framework. Here it is written out a little more explicitly. We're trying to show that that capital Pi achieves definition capital D as long as little pi achieves its definition. What's actually shown is the contrapositive. We'll show that if there, well, let me do it in two steps. What does it mean to say that pi achieves definition D? Well, in cryptography, being secure somehow means the inexistence of an effective adversary. So what we mean is that there does not exist some adversary B that breaks protocol little pi with respect to definition D. And similarly over here, there does not exist some adversary capital A that breaks capital Pi with respect to its definition. We then look at the contrapositive of this statement. We want to show that the existence of an adversary attacking the higher level protocol implies the existence of an adversary breaking the lower level one. And we create some kind of compiler, a reduction to this end, which turns adversaries against the higher level protocol into adversaries against the lower level one. Proving security for us will always mean exhibiting a reduction, transforming adversaries of this one type into adversaries of the other. In the beginning, and in the beginning I guess means the early, mid, late 80s, all the way until the early 90s, people assumed, either implicitly or in explicit statements, that this provable security approach was actually not applicable to symmetric encryption and other symmetric goals like message authentication. And the reason it was assumed that provable security was not really applicable to these symmetric aims was that usually we're starting from a finite object. We're starting from a block cipher. It takes, for example, 128 bits of message and key and turns that into 128 bits of ciphertext. As a finitary object, there certainly exists another constant time adversary that does a good job in breaking it. The way we were formalizing security and dealing with cryptography throughout the 80s and early 90s always began by postulating the existence of a security parameter and saying that security meant the inexistence of an efficient adversary, efficient meaning polynomial time in the security parameter, or describable by a polynomial-sized family of circuits, which in the limit broke this construction. None of this makes sense if you're trying to attack something like DES, the data encryption standard. It is not an object plucked from some infinite family of objects parameterized by some security parameter K. There does exist an adversary A which efficiently breaks this primitive, where efficiently here means constant time. This whole way of thinking, though, was really completely wrong. You can deal with finitary objects in the provable security tradition very much as we deal with infinite, that is, security parameterized families of objects. Here, a moment ago, we spoke of exhibiting reductions that turn adversaries of one type into adversaries of another. We can do the exact same thing in the symmetric setting when we are dealing with modes based on finitary objects and finitary objects like the block ciphers themselves. We'll exhibit these reductions, and those reductions prove security without our ever worrying about defining what is a secure block cipher, what is a secure symmetric encryption scheme. Rather, the notion of security becomes a purely quantitative one, not a binary choice. We don't speak of a block cipher being secure or insecure. Instead, we speak of how good a job a given adversary does in breaking this block cipher. We map the block cipher and its adversary to a real number, and that is the notion of security. Okay? So I won't describe this viewpoint more philosophically than I just have. I think in doing this by way of an example or two, we'll see that there's just no difficulty in bringing symmetric primitives into the umbrella of provable security. Okay, so I've just finished my brief introduction, and I told you at the beginning that we would be doing a variety of encryption goals. I want to start with the classical one. The classical one will be probabilistic security, semantically secure under an adaptive chosen plaintext attack. I'll try and sketch in a little bit why this became the classical view of what an encryption scheme was supposed to achieve. It'll take us a fairly long time to develop this classical notion of symmetric encryption scheme security, but once we've done that, I'll abandon it and redo it from a somewhat different starting point. I'll describe what I'll call non-spaced and authenticated encryption schemes. When that's done, I thought I would try again, and we will develop a notion for format-preserving encryption schemes. I suspect this is all I'll have time for in my 2 hours, but I've also prepared a section on a symbolic approach to dealing with encryption. This symbolic approach, nonetheless, being well connected up with the provable security paradigm that I described already. All right, so let's jump into it. I'm going to give this provable security treatment of symmetric encryption as was first done in 1997 in joint work with Mihir Bellari, Anand Desai, and Aaron Jacopi. The notion that I'll describe comes from Goldwasser and Macaulay's classic treatment of probabilistic encryption in the public key setting. In fact, fundamentally, we do little more than to lift the notion which had already been worked out in the public key setting into the symmetric one. Well, in the public key setting, what Goldwasser and Macaulay argued was that good encryption could not be deterministic. In particular, if you had taken a message and encrypted it, and taken another message and encrypted it, if we were using deterministic encryption, we would reveal in the ciphertexts the equality of the corresponding plaintexts. This is partial information which we should not be revealing. Therefore, our encryption scheme must be probabilistic. We will question whether or not the reasoning I just said makes any sense in a little bit. But for now, that was the story. In the public key setting, we had different keys to encrypt and to decrypt. But in this symmetric one, there will be a single key K which transforms our plaintext M into our ciphertext C, again using these implicit coins. How does decryption look? Decryption turns the ciphertext C into the plaintext M, again under the influence of the key K. In our formalization of symmetric encryption, we chose to make the decryption algorithm deterministic. Why? Well, one could have made the decryption algorithm probabilistic, just like the encryption algorithm. But in actual instantiations, it doesn't appear to be useful to do so. Furthermore, if we did admit coins into the decryption algorithm, then presumably simple statements like when you encrypt something and decrypt it, you get back the same plain text, now become probabilistic statements that this is what usually transpires. We didn't want to deal with this complexity, and therefore the decryption algorithm was assumed to be deterministic. Let's now formalize quite precisely what is the syntax of an encryption scheme, trying to keep out of our mind any ultimate intent to define security. Well, I'm going to say that a symmetric encryption scheme is a three-tuple whose components are a key generation algorithm, GEN here, the encryption algorithm, ENC, and the decryption algorithm, DEC. Okay? I've already made important decisions in writing this one statement down. I've decided, for example, that the components of the encryption scheme are algorithms and not functions. What is the first piece, the key generation algorithm? It's a probabilistic algorithm. What do you feed it? You feed it absolutely nothing. I'm going to say that you feed it no input, and it provides as output a string k. Okay? That's what it is. It spits out our key k, which is just a binary string. What is the encryption component of our encryption scheme? This is a probabilistic algorithm. It's fed two inputs, a string k, which I call the key, a string m, which I call the message or plain text, and what does it output? It outputs a ciphertext c, which is either a string or a distinguished value, meaning I don't want to encrypt this. Okay? It's important for this formulation that I allowed the ciphertext produced by this algorithm to be this designated I won't encrypt this input output. In order for this to make some kind of semantic sense for us, what I would like to demand is the existence of a key space, ks, and a message space, ms, such that whenever we encrypt a key, k, drawn from the key space, and a message m drawn from the message space, we get back a string. And conversely, if we feed something not from the key space and not from the message space, we get back this distinguished bottom symbol. We could have really quite bizarre message spaces. For example, algorithms that will encrypt for you one string of length 128, but won't encrypt for you another string of length 128. This kind of degeneracy would cause definitional problems for us later on. And so I would like to demand that if one message is in the message space, then every other message of the same length is also in the message space. Now for the decryption algorithm, as I said earlier, I'm going to formalize this to be a deterministic algorithm. It takes in the key k, a string, a ciphertext c, another binary string, and it outputs either a string, which we'll call the corresponding plain text or message, or again it may output this distinguished bottom symbol. In this context, it actually seems to be much less important that I allow the decryption algorithm to output bottom. In this initial goal of defining classical semantically secure encryption. But later on, I will want the decryption algorithm to be able to output an unwillingness to decrypt the provided string. Finally, we want a natural kind of syntactic condition that the encryption scheme composed with the decryption scheme is somehow the identity. We'll formalize that by saying that if the ciphertext C produced by encrypting M under K is a string, that is, it's not the distinguished bottom symbol, then we demand that when you decrypt the ciphertext C under the same key K, you get back the message. So all of this seems very low level and boring. Why should we obsess over the syntax of an encryption scheme? Well, my claim is that that syntax, the syntax like I've just provided to you, already embodies an enormous amount of quite consequential choices. Okay? Among those is the absence of a security parameter. Okay? I didn't give the generator a security parameter k encoded in unary, for example, which I might have done. It would have been quite reasonable to do so. But I actually end up with a rather different theory if I make that choice. As I said earlier, I made sure that my encryption scheme was probabilistic. That excluded methods which were deterministic from gaining security. Well, we haven't dealt with security yet. But it certainly excluded stateful methods, for example. I didn't allow the encryption scheme to have some kind of internal state which got updated every time I encrypted. This choice is again quite consequential. There was nothing like an initialization vector in my encryption scheme. This distances us a little bit from concrete encryption schemes like CBC, cipher block chaining, which have an initialization vector. It never showed up in our theory, and so whatever something like CBC mode is, we're going to first have to massage it so that that initialization vector vanishes before we can hope to deal with it in the framework that I just described. In some sense, a choice like this is already distancing us from practical applications in which we try to explain what something like a NIST standard for CBC encryption actually does or is. Another choice that I made was that my messages were binary strings. This might not seem consequential. After all, if you have some other kind of message space, maybe, I don't know, ASCII documents, we ought to be able to embed them first as binary strings. And yet, from a definitional point of view, I think this choice is quite consequential, and it will matter in the subsequent variants of encryption schemes, whether or not we treat our messages as binary strings or something more general. I guess these are kind of descriptive claims about dealing with carefully dealing with the syntax of our cryptographic objects before we try to define security for them. I also wrote down a couple of normative claims that I really believe that when we try to treat security, not just of symmetric encryption schemes, but of any of the objects that you might want to define and formally treat, that it's really important to first provide that syntax and to keep it separate from the semantics which you're going to later put on top. Okay? Well, we now have syntax, so we can try to figure out whether particular proposed objects are or are not encryption schemes. So our encryption scheme would have to be specified by a triple, gen, encrypt, and decrypt. But I'm just going to write out the encryption part and leave it to your imagination what the corresponding key generator and decryption algorithm would be. It's not always unambiguous. For example, here, if I tell you that the encryption map takes the key k in the message m to the message m, I haven't really spelled out explicitly what's the message space, what's the key space. It doesn't matter in this example, right? The key space, let's say, is 128-bit strings. The generator might spit out a random 128-bit string. Now that's been specified. The message space might be all strings, and the decryption algorithm then does the obvious thing. So is this an encryption scheme? So saying is it an encryption scheme is only a question of syntax. Does it meet the requirements that we levied earlier for an encryption scheme? And it certainly does. This is a good encryption scheme. It may not be good from some security point of view, but we haven't introduced any notion of security as yet. Here's another encryption scheme. Now the cipher text is supposed to be the exclusive OR of the message and the key. Remember, this is stateless. Every time you encrypt a message, you're going to XOR the message with the exact same key. Maybe the interpretation of XOR here is that you use as many bits of the key as needed, the prefix of it, and perhaps the key is taken to be a very long string, and the message space is all strings of length less than or equal to that length. This, again, is a valid encryption scheme. It's a good encryption scheme in the sense of meeting my specified syntax. Here is a well-known scheme. This is CBC encryption with a 0 IV. I'm writing it CBC 0. Again, I'm just writing the encryption portion. I leave it to your imagination to fill in what the decryption, and I'm not even specifying it, right? I'm just drawing a picture, I leave it to your imagination to figure out what the 3-tuple actually might be in this case. It's again a good encryption scheme. It's easy to take this ciphertext C1, C2, C3 and produce the corresponding plain text M1, M2, M3. Here my message space would appear to be all strings that are a multiple of n bits, where n is the block size of this object E sub k, whose syntax I have not yet defined. This was a deterministic scheme. We didn't actually use the encryption algorithm's ability to flip coins. In this variant, CBC with a random IV, I will use the encryption scheme's ability to flip coins. Here, I'm going to flip n bits, and these will take the role that I call the IV, and I'll do the algorithm exactly as before, except starting the initial chaining with this value. Again, it's a good encryption scheme. It satisfies our syntax. This one is not a good encryption scheme. The encryption of the message was supposed to be zeros of the same length of the message. It's not a good encryption scheme because, well, unless my message space had only 1 point for each length, it won't be possible to recover the message from the other underlying ciphertext. I won't be able to provide this algorithm DEC. And this isn't a good encryption scheme either, but now for a kind of trivial reason. The encryption scheme I have in mind is to do this mode for the very first plain text that gets encrypted, and then to take this final ciphertext block and use it as the IV the next time around. Okay? Why isn't that a good encryption scheme? It's not a good encryption scheme because I didn't allow for stateful encryption. Yeah, we made that map probabilistic. It wasn't allowed to tuck into its pocket some value which it uses the next time around. Now, I could have expanded my notion of an encryption scheme to permit consideration of this kind of object, but I didn't do so. Okay? Speed okay? I'm not boring you too much? Okay. I'll warn you that the slides that I sent in and are appearing in your collection of material don't exactly correspond to the slides that are being projected. You should look at me in the picture, not this thing, because you'll keep getting confused. And you'll be sure that I'm wrong, because it's not the way it is in the book. I'm ready to define security now. And as I said earlier, defining security for me means mapping an adversary and a particular scheme, which I guess I didn't write down explicitly, pi, mapping that adversary to a real number. We'll always map our adversaries to numbers in the range plus to minus 1. Okay? And the interpretation that I'll always intend in doing this mapping is that the adversary is doing a great job if it gets a big number, like 1. 1 would mean the adversary is doing wonderfully. And the adversary is doing a lousy job if the number it gets is small, like close to 0. Actually, in this definition, it wasn't in 0, 1 that I associate my adversary's advantage, but rather negative 1 to 1. If the adversary gets a negative number, then in some sense it has its conventions messed up, and it should be answering 0 exactly when it had been answering 1, and vice versa. So it's doing a really bad job, you could think of, or you could think, if it had an advantage of negative 1, that it's almost doing a great job. It just has to switch its answers. How are we going to associate this real number with my encryption scheme pi? Well, I'm going to first run the generator to get a key k. This is the first part of the experiment. When I write k left arrow gen, what I mean is to run this algorithm, remember it was a probabilistic algorithm, and take a single sample from that execution and assign it the value k. Sometimes I write a little $ over the arrow to emphasize that that this assignment is part of a probabilistic experiment, but I'm going to omit all those little $ here. After having chosen the key k by running the generator, I'm going to run my adversary A in the presence of an oracle. What do I mean by an oracle? Well, this is going to be a black box to which the adversary has access. It can provide the black box, maybe I should say blue box. It can provide the box a string in this case, M. And what does it get back in response? Well, in unit time, the adversary is issued the encryption under key K of the message M. If this is a probabilistic algorithm, then what it means is we choose by sampling according to that distribution. We let C be a point determined by running with random coins this encryption algorithm on key K and message M. That was the first question the adversary asked of its oracle. The adversary is allowed to think about that. He says, the encryption of 0110 gives me 110011. In that case, I'm going to ask a next question of some other string, M2. The adversary is allowed to choose each of its messages, M, that it asks of its oracle in an arbitrary manner, dependent quite possibly on all of the other answers that it's gotten back already, and also dependent on the adversary's internal coins. The adversary A itself is allowed to be probabilistic. In the end, the adversary is expected to output a bit, 0 or 1. This quantity over here is the probability that the adversary A outputs 1 when we carry out the experiment that I've just described. Now, this value is not the advantage. Rather, the advantage is taken to be the difference between these two probabilities. This first probability is what happens when the adversary has this blue box whose description I've just given. If instead we provide the adversary this green box, we'll get a different number out as its probability of outputting 1. The green box behaves as follows. First, we choose the key K at the beginning of the experiment and leave it fixed, just as before. Next, we're going to give our adversary a box which, rather than encrypting the message that the adversary asks of it, ignores the message, well, except its length. It flips that number of random bits. Okay? These random bits have nothing to do with the message now, apart from being the same length as the message, and it encrypts that random string. It returns that to the adversary A in response to its query. We look at the chance that the adversary outputs 1 in this setting, and we compare these two values. Suppose the adversary can tell apart a blue box from a green box. Every time we give it a blue box, it answers 1. And every time we give it a green box, it answers 0. The adversary can't distinguish the colors by the kinds of boxes by looking at their physical color, right? It's a colorblind adversary. And from the adversary's point of view, the characteristics of these black boxes are identical. A question is asked, and in unit time an answer is returned according to the hidden recipe inside the box. If the adversary can always answer 1 in this case and always answer 0 in this case, it gets advantage 1. And that's interpreted as the adversary is doing great. If the adversary can't really tell these boxes apart at all, for example, it ignores the boxes and just outputs 1 in both cases, then the adversary's advantage will come out to be 0. It'll similarly come out to be 0 if it does something like ignore the boxes and flip a fair coin and use that as its output. Intuitively, we're going to think of an encryption scheme as secure in this IND, indistinguishability sense, if, as long as the adversary A is reasonable, this number is small. What does reasonable mean? Well, it's not going to be defined. Okay? That is something that separates this approach for dealing with symmetric encryption from the more classical one, where reasonable is understood to be something like polynomial time. Similarly, what is small? Again, it's not going to be defined. This again differs from the more classical approach, where small is considered to be a negligible function, negligible meaning vanishing faster than the inverse of any polynomial. There's an alternative way of describing this exact same experiment. We can choose a random key K. We can flip a bit at random. If I write a finite set over here, then this sampling algorithm doesn't mean to let B be that set. It means to let B be a random sample from that set. So flip a fair coin. If that coin happens to come out 1, then behave like this oracle. If the coin happens to come out 0, behave like this oracle, and ask the adversary, there's an error. Ask the adversary to identify the bit B. This should say A sub F outputs B. Okay? These two notions are the same up to the simple scaling factor. Yeah? In this game, the adversary's best chance, we would like to say, is a half of guessing that bit B. So we don't want the probability to be a half, that is, the advantage to be a half. That somehow has a scaling problem with the notion just described. So we multiply it by 2 and subtract 1 in order to put it back into the same interval. The notions are easily seen to be equivalent. You can play with that for a minute and produce this, this form. Y'all still with me? You're still understanding everything? You know, usually people think definitions let you come up with proofs, and that's of course true. But it's often underappreciated that definitions also let you come up with attacks. And let me use our definition. Let's exercise it a little bit to come up with some simple attacks. So why don't we attack this scheme? I called this earlier CBC0, CBC with a 0 IV. Let's show that it is insecure in the IND sense that I just described on the prior slide. Okay? What does it mean to show that it's insecure? It means to exhibit an efficient adversary A. What's efficient? Well, I don't know. It's efficient. It's simple for us to describe. Exhibit an efficient adversary A whose advantage is going to be large. And what's large? It should mean close to 1, let's say. Well, that'll be easy to do. Oh, I actually had several of these. Let's just break this one, like I said. How is the adversary going to tell apart if it has a blue box from a green box? How many questions do you think it needs to ask? This thing is behaving like this. This thing is behaving like this, except we replace each of these message blocks with random bits. Your job, your A, is to tell which of those two kinds of objects you've got. I think we'll need 2 questions. A first question could be a single block consisting of all zeros. What do we get if we ask a single block consisting of all zeros? Well, if we have a blue oracle, we're going to get all zeros. I haven't said what this thing is. Let's say it's the best block cipher we could hope for. It's like a random permutation for each key k. So we apply our random permutation for each we apply our random permutation to zeros, and we get back a uniform random value. If we have a blue box, when we ask the 0 block, we're going to get back a uniform random n-bit string, where n is the length of the input to this block cipher. On the other hand, if we had had a green box and we asked zeros, we would have replaced those 0 bits by n uniformly chosen random bits. We'd hit those uniform bits with our random permutation, and we'd again get n uniform random bits. So if you ask one question, you'll see the exact same distribution on responses, whether you have a blue box or a green box. But if you ask a second question, you can now tell apart very well whether you had a blue box or a green box. What second question would you ask? The same question. Ask all zeros again, n blocks of zeros. If you have the blue box, you're going to get back the same n-bit value. Whereas if you ask the green box, the very first step was to choose a uniform random value up here. The chance will be only 2 to the minus n that you get the same value as you did a moment ago. As long as you do get a different value, you will definitely get a different value over here, because this was a permutation. And therefore, with probability 1 minus 2 to the minus n, we're going to get back a different value, C1, than we got back a moment ago. Well, my advantage is the probability that you output 1 when you're in this setting, minus the probability that you output 1 when you're in this setting. The first is the number 1. The second is the number 1 minus 2 to the minus n. Our advantage is going to be 1 minus 2 to the minus n. Sorry, the the chance that we output 1 is 2 to the minus n in this setting. We only output 1 if we got the same value back in response to the first and second queries. And therefore, we have an advantage very close to 1, 1 minus 2 to the minus n, by an adversary which is unequivocally efficient. It asked 2 queries and then compared them, their responses. We've broken CBC with a fixed IV of 0. Yeah.
And again, how to take M2?
We never even used M2. So my adversary A worked like this. It has an oracle F, which is either going to be that blue oracle or the green oracle. The adversary asks 0 to the n and gets back some first message block, M1. I'm sorry, gets back some first ciphertext block, C1. Then it asks 0 to the n again. It gets back C1 prime. If C1 equals C1 prime, then my adversary A is going to return 1. Otherwise, it's going to return 0. And the argument I just gave says that this adversary gets advantage 1 minus 2 to the minus n, n being this length. Clear? We can similarly break CBC with that IV chaining that I described earlier. Well, that didn't actually fit into our syntax, as I said, but we could expand our syntax, and having done so, we would be able to expand this, this notion of security to encompass it. So we won't actually go through that, but how to change the syntax, those should be XOR symbols. Do you see how to attack it? Now we're getting to something that actually is usefully broken, right? CBC with IV chaining is actually a mode of operation that has been used in the past in standards. It's a suggested way of using CBC to encrypt in Bruce Schneider's book, for example. So, and we're breaking it kind of trivially just by knowing a definition. You see how to do it? We'll ask a first message, M1, which is all zeros, just as before. We'll get back IV and C1. What would you like to ask as your next message in order to give you high advantage in distinguishing this mode from the fake version where random values are used in lieu of the message blocks? I think I heard somebody mumble it.
C1 plus IV.
Yeah. So this thing spat out IV C1, and we know that C1, and we used a message block of M1, so we know what was actually fed to this block cipher if we had the left oracle. What was fed is IV XOR M1. M1 was all zeros. So what was fed here was IV. And IV encrypted to C1 under the block cipher. Well, if we have a proper encryption oracle, then the IV is now going to be C1. That's my that's how this mode behaves. So I want to ensure that the input going into this block cipher is as it was before. So I will use IV XOR C1 as my message block M1 here. That will cancel this, and I'll get the exact same value C1 out again if the oracle was the left oracle, the blue encryption oracle. Okay? Clear? Maybe I'll write it down again. Or did I write it here? No. Oh, I wrote the whole mode, though. So that was the mode.
IV generated randomly.
It is.
You fix the plain text.
The very first message, we generate the IV randomly, and thereafter we just use our last ciphertext block as the next IV. Okay, that's what this is illustrating. I guess that should have a prime. Okay, we only use the random bits at the very beginning. Thereafter, we keep chaining from the prior last block of ciphertext. So how did our attack look? Here's my adversary A with its oracle F. We're going to ask 0 to the n and we'll get back some value IVC1. Okay? And I'm going to make the comment that the value that was fed into the oracle, EK, is IV, E sub k of IV, which I know to equal C1, if I have the blue encryption oracle. So next I will ask what string? C1 XORed with IV. If I ask C1 XORed with the IV, the new IV comes in, it cancels out with C1, and IV is the value that is fed into the first block cipher call. And so if I have the good encryption oracle, E sub k of IV is what I'm going to apply the block cipher, IV is what I'm going to apply the block cipher to, and it'll again equal C1. So this results in IV prime, which I know is going to equal C1, and then C1 prime. Finally, if C1 equals C1 prime, I'm going to return 1, else I'll return 0. Okay? We broke the scheme. It was easy to break the scheme once you really internalize the definition. And I think this is an important advantage of having definitions not only in the symmetric setting, but throughout cryptography. Often they make attacks easy to find. Okay, so I would also like to be able to prove that some methods are secure, and to that end I need to provide you that little definition, little d, right, and the little protocol, little pi, from my earlier slide. I'm always going to use the same notion of security and the same primitive. I'm going to assume a block cipher, E, just as I've been doing so far in my examples. A block cipher I'm going to formalize the syntax of to be a mapping, an algorithm if you like, from, let me define it actually as a function this time. A function from the key k to an n-bit string for some value n to another n-bit string, subject to the constraint that E sub k, that is the value we get if we fix this first argument to be any value capital K in cal k, that mapping is always a permutation on n-bit strings. Okay. What are some examples? Well, things like DES or AES are of course block ciphers. And again, just as before we have degenerate examples, the identity map E sub k of x equals x for whatever key space you like, that's also a perfectly good block cipher in the sense that it meets our syntax. Okay. I do expect that this function to be computable by an algorithm, but I'm not actually writing that out here. Okay. Well, that takes the role of the syntax of a block cipher. We have yet to define the security of a block cipher, and here's how I would like to do it. Just like for our encryption example, we're going to assume that block ciphers, that our adversary A is presented with one of two kinds of oracles, a blue oracle and a green oracle. My adversary A is going to be allowed to ask adaptively some sequence of queries, x1, x2, x3, to its oracle, and those queries will be answered, if it has a blue oracle, by enciphering each of them according to this algorithm. We simply apply the function. If instead the adversary is presented a green oracle, then we will choose a random permutation pi at the beginning of this experiment. Pi is a map from n-bit strings to n-bit strings. The adversary will ask its sequence of queries and get back pi, a random permutation applied to each of those strings. The adversary's job is to try to figure out if it has a blue oracle or a green oracle. So we look at the probability that the adversary outputs 1 when presented this guy, and we subtract from that the probability that the adversary outputs 1 when presented this guy. Again, if the advantage is close to 1, we think that our adversary is doing well. If the advantage is close to 0, our adversary is doing badly. This is called the PRP, or pseudo-random permutation, notion of security for a block cipher. There's also what I'll call the strong PRP, or the chosen ciphertext attack secure PRP notion of security. Here we provide our adversary not just the one oracle, but also its inverse. Okay? When I say the inverse of one of these, I mean for each key k, we take the inverse of the corresponding permutation. The adversary is either given the encryption and decryption oracle with a random key k chosen at the beginning of the experiment, or instead we choose a random permutation pi at the beginning of the experiment, also from n bits to n bits, and we give our adversary the forward and backward direction of that uniformly chosen permutation. This is perhaps not the first notion of security that one would come up with if you were trying to define what a block cipher is supposed to do. In fact, if you look at the early cryptanalytic literature, it deals almost exclusively with key recovery as the intended goal of an attack. Why didn't I say that the goal of a block cipher was to hide the key k, for example? That would have been a more natural thing to do. In fact, there are lots of more natural things to do. I might have said, for example, that if the adversary asks a bunch of questions, then it can't predict what the answer to a new question will be. That would have been another simple, maybe more intuitive notion of security to use for a block cipher. The answer as to why we like this PRP notion, or the strong PRP notion, is basically a lot of experience. That if we use this notion, we're going to be able to construct efficient and useful things. And if I use something like the notion I just described, either of them, can't recover the key or can't predict the next message, it will not be easy, or maybe not even possible, to construct efficient and correct schemes. For example, that can't recover the key notion is definitely way off. I mean, remember our example that the block cipher is the identity function? Well, if the block cipher is the identity function with a long uniformly chosen key, your chance of recovering the key is 2 to the minus k, where k is that key's length. So you can't recover the key, and intuitively that block cipher is terrible. When we use notions like the can't predict the next message, it will be possible to construct schemes, but they'll be very convoluted and inefficient. Finally, the cryptanalytic history of various block ciphers like DES or AES suggests that this is not an unreasonable thing to be assuming about a block cipher, that it is secure in the PRP sense. And in fact, by this point, I think that cryptanalysts have also gotten the message, and it would definitely be viewed as a successful attack if you didn't recover the plain text, or you didn't recover the underlying key, but you did distinguish the object from a random permutation. Okay. Now I have all of my 4 components, right? I have a definition for the primitive and the semantics of the primitive, both the syntax and the semantics of the primitive. I have the syntax and the semantics of the higher level goal, the encryption scheme. So if I want to state a theorem, here is the general picture from before, and here's what it comes to when I substitute in what it would mean to prove CBC encryption with a random IV, for example, is a good encryption scheme under the assumption that the underlying block cipher is a good PRP. I believe that's true. And this theorem would be a way of demonstrating it. If I can show, what am I trying to show? That if E is a good PRP, then CBC $, based on E, is a good IND secure encryption scheme. In other words, if there does not exist an adversary, if there does exist an adversary that breaks CBC $, the higher level goal, the encryption scheme, as an IND secure encryption scheme, then we've got to exhibit an adversary B that breaks the underlying block cipher E as a PRP. You need to provide for me this reduction, this compiler, which turns your encryption scheme attack into a PRP attack. Well, how are we going to do that? So here's a picture again of the scheme I'm trying to demonstrate security of, specialized to 3 block inputs. The first step is going to be to replace. So I'm now giving you an outline of the proof. I'm showing you how to turn the one kind of adversary into the other. The first step is to take my scheme my encryption scheme, $, which had been instantiated with the block cipher E, I'm going to imagine replacing that block cipher by a random permutation pi. Okay? This is the standard first step when we try to prove that some mode of operation is secure. We abstract away the block cipher by just treating it as a random permutation. This seems like a good thing to do because, well, our PRP notion of security is going to tell us that had we used a good block cipher E, then it shouldn't matter. It shouldn't be distinguishable to the adversary if that block cipher gets replaced by our random permutation pi. Having made this substitution, there will be no more kind of complexity theoretic arguments. At this point, we will be giving a purely information theoretic result. We want to show that this object, which is what the blue oracle would be, now provided a random permutation pi as its underlying block cipher. We want to show that it closely resembles, well, do you remember the definition? The object where we don't encrypt the messages that are asked, but instead encrypt an equal number of uniformly chosen bits. So this thing should look to an adversary who gets to ask such queries, just like this thing, where now the queries the adversary asks are ignored apart from their length, and that many random bits are provided. Well, why should this thing look like this thing to our adversary? Well, let's understand what the thing on the right looks like to our adversary. We provided to the adversary an object which starts off producing a first block that is uniformly random. What about the second block that it produces? Well, regardless of the adversary's query, we feed in uniformly chosen random bits. After we XOR it with the IV we've just selected, we still have uniformly selected random bits going in on this wire, independent of everything that's happened so far. When we encipher using our permutation pi a bunch of uniform random bits, we get back uniform random bits. So C1 is going to be uniformly random bits. Similarly, C2 will be uniformly random bits, even knowing C1 and IV, even knowing the message M1, M2 that the adversary had asked. Why? Because regardless of these values, we choose uniformly independent random bits over here, XOR them with something, get uniformly independent random bits over here, apply our fixed permutation pi, and therefore get uniformly independent random bits over here, independent of C1 and IV, independent of the message M1, M2. And so on, all the way down the line. The object that the adversary is provided on the right produces uniformly independent random bits of length, well, however many blocks the query was long, plus 1. So I would like to show that this thing is actually producing something close to uniformly independent random bits. How are we going to argue such a thing? This will be a little bit sketchy, but I think closing the gap between what I'm describing and a rigorous proof is actually quite small. First, I'm going to replace the permutation pi that I had a moment ago by a random function rho. When I replace my random permutation pi from n bits to n bits by a random function rho from n bits to n bits, I lose something. The adversary is able to distinguish the construction based on a random permutation from the construction based on a random function. But the amount which is lost, the probability that the adversary can output 1 in one of those cases versus the probability that it will output 1 in the other of those two cases, it's easy to bound. It's easy to bound by this quantity 1/2 sigma squared over 2 to the n, where sigma is the total number of blocks that the adversary asks. So here, when it asked its first message, that counts for 3 into sigma. If it asks another message of 2 blocks, now sigma is up to 5, and so on. So I replace the permutation with this random function and lose this much in the advantage. Then what? I need to measure how far away we are when rho from producing uniform random bits over here? Well, if independent values, if distinct values keep getting dropped into row,